Bioceuticals is proud to present a one-off seminar, The Synergistic Application of Herbs and Celluloids, on Saturday the 29th of June 2019 in Sydney with naturopath Dan Jones and legendary herbalist Dennis Stewart. The workshop will include treatment strategies, clinical pearls and case study discussion in this not-to-be-missed event, combining 70 years of herbal and mineral therapy expertise. For more information and to purchase your ticket, go to bioceuticals.com.au and click on the Education tab. This is FX Medicine. I'm Andrew Whitfield Cook. Joining us on the line today is Dr. Christabelle Yeoh, who moved from London, where she trained in general medicine and nutrition, to Sydney, Australia. Christabelle graduated from medicine at the University of London in 1999 and has obtained her membership with the Royal College of Physicians in the UK. She has a master's degree in nutrition from King's College, London, and after practicing hospital medicine, she worked as a general physician with an interest in nutritional and environmental medicine. She moved to Australia in 2012 and she has a strong interest in chronic disease management, neurological, gastrointestinal and metabolic health. Dr. Yeoh is on the board as president and teaching faculty of the Australasian College of Nutritional and Environmental Medicine, and that's acnim.org in Australia. Welcome to FX Medicine. Christabelle, how are you?
Hey, Andrew. I'm good. I'm well, thanks.
Now, today we're going to be talking about what we thought were only the batteries of ourselves, and that's the mitochondria, metabolism and mitochondria in fatigue states. But you've lectured on this, and these lectures were groundbreaking. I remember people coming out of these talks, and they were abuzz with what we thought we knew and what's actually being discovered about mitochondria. But first, let's review these actions, right from the Krebs cycle and electron transfer chain. Can you take us a little bit through this molecular machinery, please?
Yeah, okay, I will do. I must say that I was pretty abuzz as well when I started reading these papers about the bigger picture of the mitochondria, particularly the work from Dr. Robert Naveau and also Dr. Doug Wallace's work on the mitochondria is just pretty outstanding, really. So I'll just run through the basics. Essentially thinking about the mitochondria as the very crux, the very basic of what can drive life, and it drives everything. We think of the mitochondria as producing energy, and yes, indeed it does, but it's not just all that it does. It does a heap more things. But if we're just talking about energy, we can think of the energy production at 3 levels. And in fact, 2 of those levels don't occur in the mitochondria. And that's what's so interesting. So in energy production, the first level is glycolysis. And that occurs in the cytosol of the cell, not in the mitochondria. And you can get a bit of energy out that way, and then from glycolysis you go from glucose to pyruvate, and then pyruvate will enter the mitochondria then to enter the TCA cycle, as it's better known these days. And from there you get more energy production, or you get really the production of NADH and FADH. And from there, then that enters the electron transport chain, which is on the inner mitochondrial membrane. And really there is where lots of the magic happens, where you get electrons moving from one enzyme to another, and hydrogen being pumped out of the mitochondrial matrix into the inner membrane, like the intermembrane space of the mitochondria. And then that hydrogen wants to be pumped back into the mitochondrial matrix through a very special shuttle. And that is where this ATP production can occur.
Yeah, I've been watching some beautiful movies on YouTube that graphically illustrate in a moving way rather than our normal static way of studying textbooks, the ways in which the different complexes are placed in the cell, in the machinery, so that the electron transfer chain works. It really interested me that this space between them is required so that electrons don't jump too much.
And so those electrons literally have to pass hand to hand, one to the next, to the next, to the next. And so if one hand is full and can't receive the electron from the other hand, you
Doesn't
get
go.
this it doesn't go. You get this leakage, and that's where you get more reactive oxygen species and the so-called oxidative stress forming. So that whole chain has to work in this synergy, and all that movement is pretty amazing, because also the mitochondria can exist autonomously. They have their own genome, and a number of the mitochondrial DNA contain the information to make these complexes, not all of them, but some of the critical ones. So they basically can regulate their own requirement of energy making. They don't have to rely on the nuclear genome to pass them the proteins and the molecules to build what they really need for themselves.
Can I ask you just to give us a quick comment on maternal versus paternal DNA here and how things are passed on genetically?
So what we know, what you're alluding to, essentially what we know about the mitochondrial DNA, that it's passed only from the mother. So with our nuclear genome, so the DNA in our cells, we get half from mom, one copy from mom, one copy from dad. So that's maternal and paternal. Whereas with the mitochondrial DNA, we get them solely from the mom. So I think it's incredibly complicated and interesting to understand the mitochondrial DNA mutations are really what is behind a lot of probably like the chronic complex diseases, environmental illnesses, things that seem to be, clearly genetic, but it's not just nuclear DNA genetic. There's a lot of changes happening to the mitochondrial DNA that are being passed down from mother to child.
How do we assess specific mitochondrial function, not a specific mitochondrion, but mitochondrial function in general? But how do we assess the actual function of that rather than the end thing, like I'm feeling tired, I'm fatigued, and gross muscle function, things like that? Can we assess the mitochondria themselves?
First, I think we need to make a division between assessing it on the research level and then assessing it on the clinical level.
Yes, good point.
Because on both sides, absolutely, yes, is done all the time, can be done. But on the clinical side, that's where we have to make a lot more assumptions and collection of a wider range of data to make you make an assumption that there's a mitochondrial dysfunction.
So surrogate markers?
Surrogate markers, as well as so not just laboratory surrogate markers, but clinical questionnaires of symptoms and collections of symptoms that then make you realize, well, there's definite, neuroinflammation here. And in my book, anyone who's got neuroinflammation will have mitochondrial dysfunction.
Right.
It's just how severe is it? And then again, we have to differentiate between mitochondrial dysfunction and mitochondrial disease, which is a very much more defined genetic medical conditions, that geneticists and biochemists work with, that we're less likely to see in our regular general practice.
Can we go into a few of those things, the ways that we assess?
Okay, well, so I would just mention as well that, some of these clinical tests that could be available are not available in Australia. So some of my experience really just comes from doing some of these tests that were available to me in England, which was the ATP neutrophil tests, where I could look at what's the production of ATP like, what's the recycling of ADP back to ATP like, whether there's enough magnesium to make this process go slower or faster, what's actually stuck in terms of toxins and viral particles, what's actually stuck in the mitochondrial membranes, what's blocking the translocator proteins, shuttling electrons in and out. So, I used to do these tests, and they were pretty amazing tests, but they're not available here, so I don't want to spend too much time on them. But that's where I could really see what was happening and go into depth with the patient, because you could see improvement as we did our treatment, as we detoxed those fat-soluble toxins out of the mitochondrial membrane.
Yeah.
As we avoided those chemicals, like nickel was one really common thing. Bad fats was a very common thing. Drug metabolites was quite common as well. Anyway, so it was extremely revealing. But basic labs that can be done by everybody here, which is more like surrogate markers, would be looking at metabolic function. So metabolic function, we might just really skim over someone's lactate dehydrogenase or the AST, ALT on a chemistry panel. But those are really great markers. And if they're elevated, that there's going to be anaerobic metabolism going on, which basically means the mitochondria are blocked, because lactate dehydrogenase is the enzyme that changes lactate to pyruvate. And when it's high, then that person is in aerobic metabolism. And I didn't explain a bit more about that whole energy thing, but I did say, how glycolysis really only occurs in the cytoplasm, but the real magic of oxidative phosphorylation and electron transport chains occurs in the mitochondria. Yeah. So that glycolysis has got to go from cytoplasm into mitochondria, but it won't if LDH is high, because that's really keeping us stuck in the anaerobic metabolism where we don't need oxygen to fuel that oxidative phosphorylation and electron transport chain. So when you see an elevation in the LDH, then you know that you have to work with that person to improve their mitochondrial energy production if you're going to want to succeed to move that person towards, fat burning metabolism and generating more energy from the mitochondria. So that's a simple test, the LDH. Another simple test, CK. So it's a muscle enzyme. It's worth checking it, especially when the person's got muscle pain. It's not always elevated, right, but sometimes it is, because the muscles are breaking and then they're not able to repair themselves as quickly, when that's very classic of mitochondrial diseases as well as dysfunction.
Sorry to interrupt you, Christabelle, but would you mind just quickly differentiating between CK in gross muscle pain versus CKMB in myocardial infarction? What's the difference here? What's going on?
Yeah. So in the past, in hospital medicine, if someone had chest pain, you would ask for a CK and a CKMB, because the CK is all of the muscles and the MB is the cardiac muscle part, excluding the skeletal muscle part. But these days that's not done so often anymore, because you can request other things to pick up heart muscle damage. So in the context of mitochondria and just trying to get a quick view of, is muscle being damaged here, can't be repaired, you just can request a CK.
CK, yep.
Moving towards testing for more metabolic conditions, because if a person has got a metabolic condition like metabolic syndrome, diabetes, obesity, all that class of conditions, you might know that. It's pretty clear they've got that condition, but really anyone who's got that is going to have some mitochondrial dysfunction. So I measure them, measure markers for insulin, leptin, glucose tolerance test with insulin at each time point. And also you can do adiponectin. So leptin and adiponectin would be privately billed, but not too expensive on Medicare. And leptin resistance, certainly would indicate quite bad insulin resistance. And then if the leptin and adiponectin ratio isn't a positive ratio, it tells you that the adiponectin, which really helps with insulin sensitizing, helps to stimulate biogenesis of muscle. It really helps to balance the whole insulin problem. So you can get markers there that you can work towards improving, and you know that when you improve it with nutritional interventions and lifestyle interventions, then you'll know you're getting improvement in mitochondrial function.
So we're talking about insulin-resistant biomarkers, if you like here, the adiponectin, things like that, or metabolic biomarkers being a direct sort of surrogate of muscle mitochondrial function?
We're talking about it as being a marker of all mitochondrial function. Yes, you're right. And of course, muscle is only one part, but because leptin, for example, really induces reactive oxygen species generation in superoxide. And of course, that when you got too much of that, there's going to be mitochondrial dysfunction.
So I'm wondering here then if, insulin resistance is the, dare I use the word universal, cause of the other potential canary flags, if you like, of mitochondrial dysfunction, things like, slower thinking and brain fog and things like that. Are we then looking at insulin resistance as the core baddie that we've got to sort of look out for?
I dare say you would be right, like without wanting to jump to research conclusions, because, researchers may have a very strict definition versus myself as a clinician, but I'm in your camp that, in almost all our patients we see today in the clinic, you can do a lot of work towards improving the metabolic syndrome, either the risk that they have towards it, because we're all at great risk now. We all either have a medium to high risk or very, very high risk, in my opinion, because the metabolic syndrome is driven by environmental toxins, which are basically stuffing up the mitochondria. So pretty much whether you've got someone with mild fatigue, bit of cognitive dysfunction, or quite severe end of the spectrum, there's a lot of work to be done in improving the metabolic features here.
And when you're talking about the metabolic features, if we're talking about somebody who's got fatigue, is the treatment exercise? I know there's that chronic issue with chronic fatigue patients, and that is that mindset of as soon as they feel better, they'll go out and overdo it. And I've debated with Dr. Mark Donoghue about this, and he says, well, wouldn't you? It's been so frustrating in the very little exposure that I've had in treating CFS patients. I'm not an expert by any means, but I've been frustrated continually by their lack of the understanding of the word pace.
Yeah.
So how do you metabolically correct this and also teach your patients settle down? Just pace yourself. How do you do this?
So, this is what I love. But back to your question, you said, well, is the treatment for fatigue or chronic fatigue exercise? And if we want to just ask a reductionistic question, my reductionistic answer is no. No, it's not. But so this is where, again, you build the context of understanding the mitochondria and fitting it all in. So back to the mitochondria then, because this feeds back directly into your question. We said, yes, mitochondria make energy, but actually energy doesn't only come from mitochondria. It can come from glycolysis, and you can be stuck in it. But then even before the energy production, the mitochondria's first and foremost primary need of what it has to do is to balance oxygen. And it's the mitochondria's job to be able to form an oxygen gradient intracellularly, and that's really what drives this life and can generate a whole thermodynamic potential to drive cellular work. And it's oxygen and a balance of redox. So reduction, oxygenation, or oxidation reactions, that's really what allows us then to drive more energy. So if the redox is not balanced, the oxygen usage is not balanced, we just keep in a very shallow level, low level of energy production of glycolysis. So if someone is stuck in that, and then you ask them to exercise, that's just not going to work because they're driving more anaerobic metabolism, causing more lactate or lactic acid, causing more muscle burn, like doing that sprint.
Yep.
They're okay to sprint, but they can't do the marathon. And that's exactly what you're saying. Like, how do you pace yourself to do the marathon and stop crashing and burning after doing a sprint? So that goes back to, okay, well, so why is this energy production, why is this mitochondria not able to go into oxidative phosphorylation and electron transport chain? So then that comes back to, well, what is actually taking away electrons from that whole system? And what takes away electrons from that whole system, you could call it metabolic steal, and there are all these thieves stealing metabolic energy and taking away electrons. That's basically toxins, and toxins are heavy metals and chemicals. That's one massive category. The other massive category is microbes. So viruses, particularly, as highly evolved organisms that we are, we basically had to evolve to survive from viruses, and they're trying to steal our electrons, and we're trying to block them and take it back. And we've got all these mechanisms to block them, and they're really great mechanisms. They change the cell membranes, they change the mitochondrial membranes.
Change our DNA.
Change our DNA, yeah. But then when that fight is becoming a long fight and not a quick, acute one, it's chronically taking away energy from our cells, taking away electrons. So toxins, one big category, microbes, one big category. And then the other big category is basically, if you like, nutrient excess. So nutrient excess is not just saying, oh, you eat too much or too many calories. It's just on a redox level. It's just like not the right balance of nutritional input into what can go through the energy cycle.
Yeah.
So the more we eat, the more energy we need to burn. So are we eating the right things? And this comes down to the macronutrient ratios.
I'm really interested in that viral thing. Are the viruses therefore evolution's way of telling us, guess what, you're mortal? They join with our DNA, like EBV, CMV, all of these viruses join with our DNA. Herpes virus, if you're unlucky to contract that. And then they can at while stuff up our machinery given a perfect storm of inflammation, hormone, stress, and da-da-da. So is this what's happening with your chronic fatigue patients? Not just viruses, there's obviously other antecedents, but are we looking at this perfect storm, and that's the trick is to pull apart the perfect storm, what's causing it?
Yeah, we all know about all these perfect storms and vicious cycles in biochemistry and physiology, but yeah, absolutely. This is a bit of perfect storm and trying to tease it all apart. But with the pathogens, it's primarily intracellular pathogens.
Right.
That therefore we say viruses because the viruses are intracellular, but you can get other intracellular ones like chlamydia pneumonia and mycoplasma pneumonia. These are the really known ones that cause chronic fatigue syndrome. And that's exactly why it does that, I think. And so let's differentiate between chronic fatigue syndrome and just fatigue, because so far a lot of what we've said is really applicable to all of it, fatigue and chronic fatigue syndrome, in terms of trying to move glycolysis into oxidative phosphorylation, testing for it. So what we've said is applicable to it all, but the very interesting thing about proper chronic fatigue syndrome in terms of fitting that criteria, because, it's the strict definition of three things. So there's reduced capacity to do what you need to do, whether it's work, go to work, exercise, just functioning day-to-day life. Then the next thing would be post-exertional malaise and symptoms. And then the third thing would be unrefreshing sleep. So to fit the criteria of CFS, you need to have those three things for at least 6 months. And then 1 out of 2 other minor symptoms. And the one would be cognitive impairment. And the second would be orthostatic intolerance, which is when you can't keep your blood pressure up just standing still and then feeling a bit dizzy from it.
That's interesting. I haven't heard of that one. Orthostatic intolerance.
The severe form of orthostatic intolerance is also known as POTS, which is postural orthostatic tachycardic syndrome. So to have CFS, then a person's supposed to have all those major and minor criteria. And the work from Robert Naveau really shows that these people with CFS really have very special situation going on a metabolomic level that really identifies them quite differently to just other inflammatory situations and other metabolic syndrome situations, because, we said there's a lot of crossover there. And I don't think that we really understand why this is the case, but you can certainly see that it's likely to be the person has gone into what Dr. Naveau calls like an oxidative shielding situation. And that comes back to what you were saying, or what these viruses telling us. I think they're basically not telling us that we're a lesser life form than them, but actually they're teaching us that we need to adapt with our environment. And for better, for worse, we adapt in different ways.
Yeah.
And the chronic fatigue syndrome patients have gone into this adaptive state whereby they would just survive and survive and survive, but they survive with very minimal capacity to do things. They're not going to go out with a bang, like in metabolic syndrome and diabetes and type 2 diabetes, and you can get very acute organ failure and, and early demise if metabolic syndrome is not treated. But chronic fatigue, they somehow gone a different way whereby they're just going into hibernation.
Yeah.
They're going to hang in there and survive, but hibernate and can't do much at all. And that's why they're forced to pace themselves.
This is really interesting about oxidative shielding. I've glanced at, I haven't studied it, I've got to say, this patient by Naveau, metabolic features of the cell danger response. Can you take us a little bit through this cell danger response and the oxidative shielding that happens?
Yeah, okay. So cell danger response. Now, firstly, at the beginning, we said, okay, mitochondria are not just for energy. Mitochondria are critically for balancing oxygen and redox. And it's that redox balancing then drives what we call innate immunity. So in my talks, I say mitochondria, basically first and foremost, they help us with our immunity. And that's where the cell danger response fits in. So innate immunity is like an intelligent system, in that it is a kind of, in that the manner of response is relevant to the magnitude and the duration of the threat. So, if possible, the threat is dealt with within the cell in which it is detected by the mitochondria. And the mitochondria will make these danger signals and want the cell to restore homeostasis. And these danger signals are, everybody knows what cytokines are in the immune system driving inflammation. The mitochondria have exactly the same mitokines, so they are their own cytokines to drive inflammation in themselves, because they're just trying to kickstart some repair and regeneration and mitophagy or autophagy of the mitochondria, whatever it needs, it's trying to fix itself up and get rid of the threat. But if the threat is just chronic and it's just ongoing and the cell danger signal can't clear the problem and it's not successful, then an inflammatory response is then instigated at restricting the spread of the threat by elevating more degradative pathways and sensitizing the neighboring cells as well. It's telling all the other cells to shut down its cell membranes, keep the doors closed, don't let anyone in, don't let anyone out. And then it's trying to recruit specialized cells to the site of where that danger is. So the cell danger response is basically like a big alarm system going on to call all of, friends and help, basically.
Does it end in, though, like a recruitment, if you like, of control of a viral infection, like the complement system? Or does it end in other more dysregulated responses?
I think that balance basically comes down to a whole number of factors. Simplistically put, it will end when the danger is removed.
Right.
So the cell danger response will only stop when the threat is removed. And so if the threat is just a virus, and most of us can just get over a virus fine, or if a threat is an intracellular pathogen, and maybe we use some antimicrobial therapy to help our bodies and we got over it fine, great. But if a threat is, chronic ongoing toxin exposure, and, that doesn't happen overnight, right? So that's always there. But if a threat is also the nutrient excess, like carbohydrate loading, and I said just now that the more we eat, the more more energy we burn. I didn't mean just so much in terms of we need it to exercise, but the more we eat, the more reactive oxygen species are made in the mitochondria as part of processing the energy. So the more we eat, then the more work the mitochondria has to do. Then, so it's a bit like if our cells are under siege, because it's under siege and threat by bad nutrients and bad toxins, and then it's at war as well with viruses, then it's just being overwhelmed.
So I guess a differentiation might be if you have a viral infection, at least if it's working correctly, the body can initiate the complement reaction and that sort of thing to set off hand grenades to explode cells and kill the local area, set off a bomb in the local area, ends up in some local destruction, but hopefully the resolution of the viral infection. But how do you kill a toxin? How do you kill mercury? How do you kill a persistent organochlorine pesticide? Is this what's going on?
This is exactly what's going on. So in a number of my talks as well, I have previously talked about, immune dysfunction and what's happening in the microglia and what's happening in the dendritic cells. So the antigen-presenting cells and dendritic cells, and in the brain, that the equivalent of that is the microglia. If they're just chronically being overloaded and overexposed to environmental stimuli like chemicals, then you already have this priming and already this background activation of these cells. And of course, in the brain, we know about microglia. And if you're priming the microglia, and that can already happen in utero, for example, then you're getting these kids born with already primed brains, ready to overreact and overrespond to what might normally be a typical acceptable environmental challenge, an infection, taking too much Panadol, whatever it might be. Normally we can deal with that, but if you're already primed to the near threshold and then get a few more triggers and go over threshold. So yeah, absolutely, that's the problem, and that's why it's happening intergenerationally, and generation to generation we're having more and more autoimmune and more neuroimmune and neuroinflammatory conditions.
Okay, so is there any way to tease apart who might be at risk of these? I know in utero is obviously an impossibility to assess the fetus themselves. Could one look at the mother or the infant to look at either gross signs like, musculature, muscle tone in the newborn or the infant, and perhaps aberrant immune signalling or something in the mother? Is there any way that we can tease apart those infants that might be at risk?
So first, looking at the mother's side, so getting a really good family history. Does autoimmune really run through the family already? Do neurodegenerative conditions run through the family? And if it's yes and yes on both or either, yes, that's already a big maternal risk.
Yeah.
And allergies and immune deficiencies as well. But the more environmentally challenged ones would be the autoimmune and the neurodegenerative. And then with the child, I suppose if a child already clearly has low tone or hypotonia, that is a very clear flag for mitochondrial dysfunction.
Right.
And maybe I think many parents might just be told, well, I think they wouldn't even be told if this is hypotonia. They might just go, a bit floppy.
Mm-hmm.
And everything else seems fine. Baby sleeping fine, feeding fine, pooping okay, no real concerns there. I think looking through my eyes, I would worry, and I would think, well, do I need to do tests? Should we do some urine testing for amino acids, organic acids, some blood testing to look at other, muscle enzymes? And that's really, it's very hard to say this on a population level because you can't just test everyone, but just on I'm a clinician, so I go very much on a one-to-one level.
Yeah.
And if someone came to me and said, well, my baby's 3 months old and, seems to be a bit floppy, everything else is fine. And then I found that the mother family history is not good, then I think I would test.
Yeah. And I didn't ask this earlier, and I guess I should have. When we're looking at these surrogate markers of mitochondrial function, how do you tease apart the more obvious things? I guess now that I ask it, it's probably a more obvious question about things like how do you differentiate between, the obvious ones like iron deficiency or the more insidious things like depression-related fatigue?
I would be, before making the diagnosis of chronic fatigue syndrome and just assuming there's a problem in the mitochondria, one assumes that all of the normal medical tests have already been done to exclude, iron deficiency, exclude thyroid disorders, anemia, just a full chemistry, blood panel, all of the things that regular GPs would have done. So, you have to exclude that. But really, right now, chronic fatigue is just a condition of exclusion and meeting those criteria. So what is done in the research now isn't done in clinic, and then would be shifting across to, well, what are my own clinical signs of looking for mitochondrial dysfunction so I can make some baseline so we can work towards it. But mitochondrial disease, like a child that has hypotonia and maybe is going to develop a real serious genetic condition, those disorders are tested through muscle biopsies, genetic tests, amino acid testing, organic acid testing, and that is done in hospitals.
Yeah. Just getting back on to chronic fatigue, and I guess we're going to be mainly treating adults here, or at least teenagers, not babies. But can you give us just a quick few tips on general treatment aims?
Okay. I'll answer this question in 2 bits because that's big. So one bit will be the overview approaches, and then the other bit, I'll give you a little tip on just one of the tiny details in that overview. So the overview, I would say the biggest thing is really it's coaching coaching and education around understanding, our mitochondria, what they're there for, what they're doing, and what we are doing that's causing a whole mitochondrial mismatch. So those big categories would be what are the toxic exposures we are facing, and what is everything we can do to minimize, avoid, and remove the toxins. And then the second thing is what are the other factors taking away the mitochondrial energy, the metabolic steel, and that's microbes. And so what can we do to help the person reduce a viral load, reduce an intracellular pathogen load? And then the third big category, actually it's 4 categories. So the third category would be what can we do around balancing the stress of having to metabolize food. So of course we need to eat. So how are we best going to eat? How can we adjust the macronutrient ratios? How can we factor in intermittent fasting? How can we change things up so that the mitochondria can do minimal amount of work for maximal amount of output? And then the final 4th category around the coaching and education is what are we doing with our movement and exercise that's either putting too much strain or not enough demand on the system.
Yep.
So those would be all those big categories.
Yep.
And for the little tip, so for the little tip is fats and phospholipids. So, okay, that's a little tip, but actually it means a lot. It
means a heck of a lot, yeah.
Yeah. So phospholipids would literally be take phospholipid supplements, and there are a couple of really good ones out there that are really geared towards helping with fatigue. So they're mitochondrial nutrients that include phospholipids, glycosphingolipids, sphingolipids, things like that.
Mm-hmm.
And then so that's one aspect of fats. And then the other part of fats that's a lot harder than just swallowing these pills is just don't eat any bad fats at all.
Yeah.
So, of course, that's a lot harder to do, but that's seriously important.
That's the equation. What about some learning or resources for naturopaths and GPs who are interested in treating chronic fatigue? Like, you're the president of ACNEM, and ACNEM does courses for GPs. What other resources are available?
I must say that how I've presented this information around chronic fatigue, thinking of the mitochondria this way, using Dr. Navo's work. I haven't seen a book yet being written about it. Some people ask me to write it, and
yes,
I haven't quite got the smarts to write a book, I'm afraid.
Yes, you have.
So I'm sorry, there isn't an easy all-in-one resources just thinking of it that way, but plenty of resources in thinking about addressing the metabolic syndrome part, the macronutrients, the fats, carbs, addressing insulin, doing nutritional ketosis where it's appropriate, intermittent fasting where it's appropriate, lots of resources around that. And then, okay, if you Google NAVAUX, NAVIAUX, chronic fatigue syndrome, there are lots of blog sites and chronic fatigue communities talking about how his work applies to them. So there and Q&A, and easy to understand information because his papers are quite dense, quite hard to understand.
Great.
So that's that, but it doesn't necessarily just lead to treatment. However, a lot of treatment of chronic fatigue is listening to the patient, is acknowledging where they sit, and it's educating them how the future is going to look, what they need to do to manage themselves. And that means already hell of a lot. So, I would suggest people do that.
Well, we'll definitely put some of those resources, including the work of Novo, up on the FX Medicine website, particularly one that I was reading the metabolic features of the cell danger response, which I thought intensely interesting. But also you were alluding in the end with the phospholipid treatment to some work that was done by Garth Nicholson and Mike Ash. So we'll also put those resources up on the FX Medicine website for our listeners. Christabelle Yeoh, I cannot thank you enough for taking us through. I mean, this is a complex web, and the talks that you've given, particularly at the Mind forums where I listened, were invaluable for me as a practitioner. So I can't thank you enough for taking us through at least some of that tip of the iceberg that presents with chronic fatigue in mitochondrial dysfunction.
Thank you for having me. I'm really too glad to share the information to people who are interested. Thanks, Andrew.
This is FX Medicine. I'm Andrew Whitfield Cook.
If you're a healthcare practitioner and want to learn more about how to develop more targeted treatments for your patients using genetic testing, then Bioceuticals DNA Testing in Practice is for you. This 10-module professional development course, presented by Dr. Denise Furness, is designed to help you unlock your patient's health potential. You'll learn how to move away from the trial and error approach that so typically leads to patient dissatisfaction to a targeted clinical model defined by decision-making that distinguishes those patients most likely to benefit from a given treatment from those who will not. For more information on the DNA Testing in Practice 10-module program, visit the Bioceuticals website or contact your Bioceuticals sales representative.